Pleased to have Meredith Hughes to speak to us today. Meredith did her PhD in Harvard, became a Miller Fellow at UC Berkeley after that, and is now a professor at Wesleyan University. She was selected as a Cattro Scholar in 2018 by the Research Corporation for Science Advancement. Her expertise is in the study of young circumstellar disks using radio interferometers. And today, she's going to tell us about using these observations to trace planetary systems. So during the talk, if you have any question, please use the raise hand function or notify me in the chat. My name is Jeffrey, and I'll find the time for you to ask your question. So with that, welcome Meredith, and please take the floor.
Great. Thank you so much for that introduction, Jeffrey. And thank you all for joining me today and for the invitation to speak to you all. I'm really, it's a pleasure to be here. So I did, just to warn you, like Jeffrey said, feel free to raise your hand during the talk and ask questions. I did also build in a few stopping points through the talk to allow everyone to ask questions. I certainly can talk over Zoom for an hour, but I prefer not to. So I hope that you will, you'll have some questions along the way as well. Today, I'm going to talk to you about using debris disks to trace the dynamics of planetary systems. And I always like to start off my talks with two pictures, one like the one on the top here, showing the science that I'll be talking about today. And this is, as we'll talk a lot more about this image later on, this is the Edge-on debris disk around the nearby young star AU-MIC. And the other picture is a picture of the technique that I use to do my science. This is the Atacama large millimeter submillimeter array up in the Altiplano in northern Chile. So today, I am going to talk to you about a few different projects that my students and I are working on here at Wesleyan related to dynamical probes of debris disks. So just to kind of take a step back and think about planet formation a little bit kind of from the ground up, I just want to remind everyone that we know a lot about planet formation just from naked eye astronomy and from constraints that we can get by looking up at the night sky. So here is a beautiful image of many objects in our solar system. And of course, we all know that they don't fly willy-nilly around the sky. They travel in this flat plane. And if you watch them from night to night, from month to month, and from year to year, you can see that they have this preferred direction where they're all moving counterclockwise around the sky from west to east every night. And then if you use a small telescope, or in this case, the Hubble Space Telescope, you can also take a look at the rotation directions of the planets and the orbital direction of the moons around the planets and notice that those are mostly the same too. This preferred counterclockwise rotation direction in the solar system extends to the rotation of most of the planets and also to the rotation direction of most of the moons around the planets. And then finally, if you really want to put numbers on this, you can also take a look at all of the asteroids and small bodies in our solar system. And I love this movie of all of the known asteroids in the solar system as our knowledge has built up between January 1999 and January 2018. And so you'll see the main belt asteroids in orange and the blue are the near Earth asteroids. And once again, I just want you to notice this preferred counterclockwise rotation direction in the plane of the solar system. So by looking at that flat plane in the sky, we see the flat preferred plane of our solar system. And then by looking at all of the objects in our solar system, including all of these near Earth asteroids and main belt asteroids in the solar system, we see that preferred counterclockwise rotation direction. And those are both, of course, imprints of the way that our planetary system formed. It formed out of a flattened disk of gas and dust, and the angular momentum of most of these objects and their orbital angular momentum was inherited from that initial protoplanetary disk. So the cartoon version of how star and planet formation proceeds is that we start with a giant molecular cloud. The densest parts of those clouds collapse under the influence of gravity, and then you ultimately wind up with a protostar in the middle, some kind of a pseudo disk at this phase, an envelope with infall onto the disk and outflows. It's very messy. I don't actually study this stage at all. I prefer to avoid it whenever possible. Then eventually everything settles down and you wind up with a pre-main sequence star surrounded by what we would call a protoplanetary disk that at this stage is mostly gas. We think about 99% of the mass is in gas and 1% is in dust. And it's more or less inherited from the previous phases of planet formation. And then eventually that more or less primordial material disperses and you wind up with something that looks much more like our own solar system, a main sequence star surrounded by a debris disk, possibly including planets. And just to, so this is the cartoon version, right? To give you, again, something concrete to have in your mind when we're talking about debris disks. So I guess I should mention, yes, that my talk today is going to focus, even though I work on both of these last two stages, protoplanetary disks and debris disks, today my talk is going to focus on the debris disk stage. That's most of what my group is actively working on right now. And again, just to give you kind of a concrete picture of a debris disk that you can have in your mind, I want to remind everybody that here in our solar system, we have not one, but two debris disks, and one of them we can see with our naked eye. This is a picture of the zodiacal light. And so if you've ever been, up on Mauna Kea at sunset, you can often see this band, this ghostly band of light stretching up above the horizon. That's not the Milky Way. It's the light reflecting off of the tiny dust grains in the inner solar system that have been created by collisions of Jupiter family comets and asteroids in the inner solar system. But if we were alien astronomers looking at our solar system from a distant star, this would actually not be the brighter of our two debris belts in our solar system. The brighter of the two debris belts would actually come from the Kuiper belt in the outer solar system. And so it's just because we're sitting inside the zodiacal light that it looks brighter to us. But really from the outside, the Kuiper belt has a larger mass and surface area of dust. And so that's what we would see. And all of the debris disks that I'm going to talk to you about today are at distances from the central star that make them more like Kuiper belt analogs. And so they're all much more massive than the Kuiper belt because given our current technology, if we were alien astronomers trying to observe our solar system from a distant star, what we would actually see is nothing because we don't currently have the sensitivity to detect our own Kuiper belt around another star. So when we're looking at the debris disks that I'm going to show you today, you should think of them as scaled up, more massive versions of our solar system's Kuiper belt. All right, just a little bit more about circumstellar disk evolution. Again, protoplanetary disks are around pre-main sequence stars. They're very, very gas rich, and the dust is more or less primordial, although it's undergoing growth. And but the processes involved in the protoplanetary disk stage, we think are more agglomerative processes. Whereas in the debris disk stage, these are around main sequence stars. We used to say that they have no gas, but now we know that some of them actually do have substantial amounts of gas, and I'll talk about that briefly at the end of the talk. And the dust, if you calculate the lifetime of a dust grain in a debris disk, it's very short compared to the age of the star. So we know that the dust must be replenished through some sort of collisional grinding mechanism. And rather than the agglomerative processes that characterize the protoplanetary disk stage, debris disks are going through this collisional grinding of material. And what we're seeing is really second generation dust that was previously incorporated into planetesimals. So if you're interested in planets, you want to know about the transition between the protoplanetary and the debris disk phase. And in particular, you want to know how long does it take for the gas especially to disperse, especially if you're interested in planets like Jupiter, Saturn, Uranus, and Neptune. You want to know how long does that gas stick around. And so that's one reason why we're really curious about this phenomenon that we've observed of gas and debris disks. So some of the questions that I'm going to try to address today are for debris disks, how much unseen mass is in large bodies? It's relatively easy for us to say how many small dust grains we can see, and we can kind of figure out how much mass that corresponds to. But what we really want to know about the planetary system is how much mass is hidden in large bodies that we can't see because they are too small for us to detect through, say, direct exoplanet detection techniques. So how much unseen mass is in those planetesimals and Uranus and Neptune analogs that might be sculpting these debris disks? Another question we have is, can debris disks measure planet masses? The answer is yes, but it's tricky, and I'll tell you a little bit about that. And then finally, what is the origin of that gas that we see in debris disks? And it's much more common than we thought it was originally. So that's something exciting that we've been learning about recently. We want to know what causes this phenomenon of gas in debris disks, and what is this gas actually telling us about the planetary system? Okay, so if I were doing this in a class, I would stop and do a little think, pair, share here. So you can just bear with me for a moment while I kind of talk through this, because I think when people talk about debris disks, I think there are a lot of misconceptions out there about what is and is not a debris disk. So all right, to what extent are debris disks? You can think about this yourself, and then I'll tell you the answer. Gas-free as far as we can detect. Okay, obviously I've just been talking a lot about gas and debris disks. So the answer here is clearly sometimes. Some debris disks we can't detect any gas, but many debris disks we do detect some amount of gas. All right, to what extent are debris disks older than protoplanetary disks. And here I've been mentioning that protoplanetary disks are mostly around main sequence stars and debris disks are mostly around, protoplanetary disks are around pre-main sequence stars and debris disks are mostly around main sequence stars. But the answer here is actually sometimes as well, interestingly enough. We now have examples of debris disks in stellar associations that are as young as 2 to 3 million years old. And we have examples of protoplanetary disks that can last for 10 million years or longer. So there's a lot of overlap, actually more than we had previously realized, in the age of protoplanetary disks and debris disks. And that raises some interesting questions about what triggers that process of converting from a protoplanetary to a debris disk and why the timescale is so different for different systems. All right, and then to what extent are debris disks optically thin at all wavelengths? So the answer to this, as far as we know, is always. This is one of the distinguishing characteristics of a debris disk. It's actually, when we see optically thick dust, we think, aha, we have found a protoplanetary disk. Whereas when we see optically thin dust, we go, aha, this is probably a debris disk. Now, there's certainly some examples with protoplanetary disks where we think that some regions might be optically thin, and we now know that the structure is a lot more complicated than we previously understood. But it still seems like a pretty good distinction overall, like if we're looking at the fractional excess infrared luminosity. And then finally, I mentioned this as well, but to what extent are debris disks undergoing destructive collisions? And we think that this is really the defining feature, the defining characteristic of a debris disk, is that it's something that has already undergone most of its planet formation and is now going through these collisional cascades, this destructive process, producing the dust that we observe. Whereas with protoplanetary disks, we think that those are more strongly characterized by agglomerative processes. And if you want to know more about debris disks, you can check out this annual reviews article that I wrote a couple of years ago now. And it goes through all of the details of the structure, composition, and variability of debris disks. And here is one of my favorite figures from the review that just shows the variety of structures in debris disks. And I'm only going to have time today to talk about a few different types of structures, but I just wanted to point out that there's enormous variety in the structures that we see in these debris disks. You can see narrow rings and broad eccentric rings, radial gaps. We'll talk about this system today, arcs, warps, asymmetries, clumps, and swept back wings and spiral arms. And we think a lot of these structures have to do with the presence of planets in debris disks. Some of the structures have really no alternative explanation other than planets at the moment, although some do have alternative explanations. So yeah, these are, the other thing that I wanted to point out about debris disks, and this is going to come up as a theme throughout what I'm going to tell you today, is that debris disks really look different at different wavelengths. And the reason for that, which I can give you the background if you want, but for now I'll just give you the rule of thumb, is we use this rule of thumb that the grain size that you're looking at is roughly equal to the wavelength of observation. So if you're looking at optical wavelengths, you're looking at micron, submicron size dust grains. And if you're looking at millimeter wavelengths, you're looking more at millimeter size dust grains. And so there are different, they're both different. So there are two things going on here. Why do debris disks look different at different wavelengths? One thing that's going on is that different physics applies to different grain sizes. So for example, the small grains are going to be more strongly affected by radiation pressure than the larger grains. And the other thing that's going on is there are different emission mechanisms and radio transfer mechanisms that are important at these different wavelengths. So for example, here, this is 3 images of the same debris disk, the debris disk around Fomalhaut. This one is at visible light wavelengths. And if you just look at where's the brightest part of the disk, it's this entire side of the disk, basically, that looks brighter than the opposite side of the disk. And so that has to do, that's a scattering phenomenon. And so this is probably forward scattering from dust grains in the debris disk. And then you go out to the far infrared and you get a phenomenon called pericenter glow. So Fomalhaut is a very eccentric debris disk. And so one side of it, so you can see this is the pericenter, right? One side is a little bit closer to the star than the other side. So the pericenter tends to glow at far infrared wavelengths through a combination of 2 properties. One is that it's hotter if the material is hotter if it's closer to the star, but also at these wavelengths, there's still a lot of kind of reflection and scattering going on. And so the amount of light that reaches these dust grains drops off as 1/r squared. And so having it much closer is going to make it much brighter than the farther away side of the disk. But then you go out to millimeter wavelengths and you get a phenomenon called apocenter glow. And this one's a little more subtle, but it's real, it's statistically significant that now the apocenter is glowing more brightly than the pericenter. And the reason for that is because at millimeter wavelengths, it's purely thermal emission, we think, from these dust grains. And so we're really tracing basically the surface density of particles in the debris disk. And because these particles are on eccentric orbits, they spend a lot less time at pericenter and a lot more time at apocenter. So you build up extra density at apocenter. And so that's why you see that extra apocenter glow, because you have more particles per unit length in this debris ring that are piled up at apocenter because of their orbital properties. So that just gives you a little bit of a sense of how we can see the different kind of radiation and emission mechanisms going on at different wavelengths. But then also it's worth pointing out, like I said, that there are these differences in the physics that are affecting the different sizes of grains. And AUMIC is a really great example of that. So small grains are particularly affected by radiation pressure and stellar winds, whereas the larger grains are more immune to those effects. And so they tend to more directly trace the gravity in the system. And so here's AUMIC. The colors here are Hubble Space Telescope observations of the scattered light from AUMIC, and the contours are ALMA observations of the thermal emission at 1.3 millimeters wavelength. And what you're seeing here is real. It's not a sensitivity effect, that the ALMA emission is confined to a region that goes out to about 40 AU from the star, whereas the small grains that are traced by Hubble Space Telescope are blown out much, much farther in this halo that extends well beyond the millimeter disk. So that's why wavelength really matters. And I'm, of course, going to focus on submillimeter observations of debris disks today. And partly that's because we're interested in tracing the density distributions of particles in these disks, which is most directly traced by thermal emission. And it's also because we're really interested in what the millimeter grains can tell us about the underlying gravitational potential of these systems and the dynamical interactions between the unseen planets in the disk and the dust that we can see with ALMA. And of course, I already mentioned ALMA is the tool that we're using here. ALMA is amazing and wonderful, and I really hope that it's going to be starting back up here in the next few weeks. They're starting to reopen the site. And just to show you, if you're not familiar with ALMA, it's an interferometer, again, located in the Altiplano in northern Chile. There are 66 antennas that you can, of different sizes, that you can spread across the Altiplano out to distances of 15 kilometers. You can see that each one up here, here's a little person for scale, and each one of these is 12 meters in diameter. The main array has these 12-meter diameter antennas. And so it's the size of a small house. And there's a transporter that picks up these antennas and drives them around the Altiplano. And why is this site so amazing for submillimeter interferometry? There are a couple of different reasons. One is that it looks, from this picture, it looks like, well, it doesn't look that high altitude because there are these high mountain peaks that you can see above it. It kind of looks like a valley with mountains all around. But that's deceptive because, in fact, some of these mountains go up to 18,000 feet in altitude. And the main plain here is at 16,500 feet, which is higher than the 13,800 feet or whatever it is in Mauna Kea. So the whole flat part is higher than Mauna Kea, and there are mountain peaks, volcanic peaks around it. So it gets you up above most of the water vapor in the atmosphere, which is the critical thing that blocks the emission at millimeter wavelengths coming from space. And the cool thing is that it's a big flat plain, so you can drive your antennas around and spread them out. It's the second driest desert after Antarctica, so we have incredibly good sensitivity, incredibly low water vapor in the atmosphere, and it just happens that it's also in a place where it's high and flat, so that you can spread out your interferometer to long baselines without driving off the edge of a mountain, which is a problem in other places. So ALMA is wonderful, and ALMA has done, it has truly, I mean, I know that people say this, right, and it's hackneyed, but it has truly revolutionized our understanding of planet formation. And I just wanted to show an example of one project that I've been involved with. This is the D-Sharp survey. And so I know that you've all seen the beautiful HL Tau image that came from ALMA as part of the commissioning of the long baselines in ALMA. And D-Sharp was a follow-up to that observation, basically, to go and ask the question of, okay, we know now that HL Tau has this beautiful ring-like structure that we had kind of imagined would be there with planets carving out gaps in the debris disk. But now we can actually follow it up for a sample of objects. So it was, you can see here, it was 20 different objects that we looked at, and we were basically looking to see, okay, how common are these structures in bright protoplanetary disks? And the answer was they're everywhere. So you just see nothing but rings and gaps in all of these different systems. We have a couple of systems where we saw spiral arms like this one right here. But the diversity of architectures and the is really impressive, and just the ubiquity of the ring-like structures is amazing. And it has answered a lot of questions. For example, the question of like, why do we even see millimeter grains in these disks in the first place? Because we shouldn't. They should have very short lifetimes in gas disks, unless there are these pressure bumps that are keeping them confined in these rings. But it's raised a lot of other questions too. And of course, the big question is, what is carving out the rings and gaps in these protoplanetary disks? So today I'm not going to talk about D-sharp, but I am going to talk about some analogous structures that we're observing in debris disks, and we're starting to be able to get the same type of angular resolution and sensitivity in debris disks that we have been able to do in protoplanetary disks. Debris disks are harder because they're bigger and fainter, so they're much harder to observe with ALMA. And the analogy that I like to give is that we're basically at the point with ALMA now for debris disks that we were with protoplanetary disks with the SMA. So we're starting to see hints of this underlying substructure. And these hints are really tantalizing, and they're starting to tell us about the underlying planetary systems. And basically, as ALMA expands its bandwidth, it's going to get better and better and better. Okay, so I guess I'll pause here and just ask if there are any questions about anything I've talked about so far. That was the background material, and now I'm going to lead into a series of 3 different projects that my research group is working on related to gas and dust and debris disks. No hands up yet, Jeffrey. Okay, I know it's just background material at this point. Okay, so I will talk about each of these 3 projects, and I'll pause at the end of each one to see if there are any questions. So the first project involves using debris disks to measure companion masses. And I'll give a little bit of the background behind the idea here. So when we think about directly imaged planetary systems, we now have a bunch of directly imaged planetary systems that we know about. Some of the earliest ones were like HR 8799, of course, was one of the first directly imaged planetary systems, and so was HG 95086 here. In this case, the stars are hidden, and we're seeing the bright spots that we're seeing are planets. And it turns out that to nobody's surprise, debris disks and directly imaged exoplanets go together. In almost all of the known directly imaged planetary systems, there's also a debris disk, often right outside the directly imaged planets. So this is great, right? This is like exciting for dynamicists and for observers who like to observe debris disks and planets, because it really gives you a wonderful test bed for looking at the interactions between the directly imaged planetary systems and the debris. So these are ALMA observations and submillimeter array observations of the same 2 systems that I just showed you, showing that debris disk outside the planetary system. And so if I take those pictures of the planetary system that I showed you on the previous slide and scale them to the scale of these images, you can see that the planets fit nicely inside these debris belts that are outside the planet. And one of the cool things that you can do is you can actually then use the location of the inner edge of the debris belt as a dynamical constraint on the mass of the outermost planet. And here's an example of that for HR 8799, where what we did was we took the location of the inner edge of the belt and used chaotic zone theory, which I'll just give you the briefest overview of on the next couple of slides. And we said, okay, what limits does this place on the mass of the planet? And so we're able to basically get this posterior distribution after doing some modeling that gives us constraints on the mass of the planet. They're not very good constraints yet, but they're an important check. And the better our sensitivity and resolution gets, the better we will be able to constrain these values. But it's important because a lot of times directly imaged planetary systems, our estimates of the masses of the planets are very uncertain. And they're not only uncertain, they're based on these difficult to calibrate models of the emission of the exoplanets as a function of not only the frequency that you're looking at, but also the age of the system, which we also typically don't know very well. So it's really very difficult to get a constraint on the mass of a directly imaged exoplanet. And this is a way of getting around that and placing direct dynamical constraints on the mass of the exoplanet. So a system that we were interested in is HG 206893. It's one of only 2 known systems so far that has a directly imaged brown dwarf companion orbiting interior to a debris belt, just like I showed you in those other systems. And the same issue applies to brown dwarf masses, where we would really like to get better dynamical constraints on a range of brown dwarfs. So we started observing this system with ALMA. Just to, remind some of you, I know many of you are bigger experts at dynamics than I am, but just to remind everyone about what the chaotic zone is, because I'm going to keep using this term. So from three-body dynamics, every companion, so here I've got, let me move people's faces. Here I've got a little planet orbiting around a star and a debris belt around it, similar to the three systems that I've shown you. So then this equation down here gives you a relationship between the distance between the planet and the inner edge of the debris belt. So assuming that around this planet, there's a range of orbital locations where the orbits are too chaotic to be stable. So you don't expect to find dust or asteroids. And then if you assume that this planet is carving the inner edge of the debris belt, this distance, delta AN, between the location of the planet and the inner edge of the debris belt gives you a relationship between the mass of the companion and the semi-major axis of the planet. So we can usually get a pretty good idea of the semi-major axis of the planet from direct imaging of the planet's orbit. And then we go out and measure the location of the inner debris belt to derive delta A. And then, we can try to figure out the mass of the star from spectroscopy, and that tells us the mass of the companion. So that's the idea here. And we see this at work in our solar system, where here's the distribution of asteroids in the main belt of our solar system. And this 2-to-1 resonance here, basically you don't see any asteroids outside of this because of Jupiter and its chaotic zone. And the clearing of the Kirkwood gaps is also a similar phenomenon. And this clearing of gaps at resonant locations with planets is also something I'm going to be talking about later. So it seemed worth mentioning that Jupiter does it in our solar system.
Meredith?
Oh, yeah, go ahead.
Jeremy has a question.
Okay, great.
Oh, just a quick question. The exponent in that relation, I mean, I suppose it's the result of some fit to simulations, but shouldn't it really be a third rather than 0.31 in the limit of a very small companion mass?
Well, yeah. So that's a good point, and that's in the so that point of in the limit of a very small companion mass is certainly true. But in this situation, we're talking about a brown dwarf, and so we're no longer in the limit of a small companion mass. And so there are a number of people who've investigated numerically what this relationship should be for different ratios of the mass of the companion to the mass of the central star. And let's see which. Yeah, this came from the Morrison and Malhotra paper from 2015, and so they have gone through a bunch of numerical simulations and looked at, okay, what happens when you start to have a more massive companion, something more like a brown dwarf. And so they actually have like a little table of these exponents looking at how it changes with the mass ratio of the companion to the star. So that's what we're using for this particular project, just because this is a slightly more massive companion, so we want to use the results that are appropriate for a more massive companion. But you're right that in the lower mass limit, it does come down to a third, or I think it's 2/7 or something like that. So okay. So moving on, so we started off trying to measure the inner radius with ALMA, but when we did that, we got kind of a surprise, because this is the image that we saw. And if you look at the brown dwarf on the scale of this image, it's teeny tiny. And so we were like, that's strange. Okay, so clearly the brown dwarf is not carving the inner edge of this bright outer belt that we're seeing. But as we started modeling, we noticed something interesting, which was that our models kept trying to extend into where the brown dwarf was. And that what would happen is we would be left with a ring of residuals at a distance of around 80 AU from the central star. And so finally we said, oh, we get what's going on here. What's going on here is that there's actually a gap in the disk. And if you don't put material in the inner system, first of all, you can't reproduce this nebulosity around the central star. That's real. And also, if you don't put material in the inner system, the modeling code will try to like double the mass of double the flux of the central star from what it should be. And that's because it's trying to make up for this extra dust emission. So we actually have dust emission in the center that's comparable to the flux of the central star. And there has to be a deficit of emission between the inner part of the disk here and the outer bright ring. And so what we're really seeing is we're seeing a gap in this debris belt. And so when we add a gap in our model, we get beautiful empty residuals that are consistent with noise. And so that's pretty interesting. So not only now are we able to place constraints on where the location of the inner edge of the debris disk is, but we're also finding a gapped structure in this debris disk that echoes the gapped structure that we're seeing in protoplanetary disks. And this is a very recent phenomenon. And in fact, there are only 3 other systems, all of which have been published within the last 2 years, showing gaps in debris disks. So the 3 other systems are HD 15115, HD 107146, and HD 92945. And you can see in each of these, HD 107146 is the most beautiful, glorious example of this, where we really have excellent high signal to noise observations. And this is a sun-like star, I might as well point out, where we have this brighter inner ring, a fainter gap between the two, and then another brighter outer ring here. And so we now add HD 206893 to this list of planetary systems. And so the question is, what is carving this gap? And so there are a lot of different things that could do it. And so the first thing that we checked, obviously, was, well, could it be some kind of resonance with the brown dwarf in the interplanetary system? And the answer to that is no, it can't. It can't have anything to do with the brown dwarf. Even if you basically pump up the eccentricity as much as the observations allow, it can't clear a gap out at 80 AU. It's down at like 10 AU. So there are various explanations that have been proposed in the literature. And one thing that my student Anna Fair did, and by the way, I can mention that these are amazing young students that I have. Ava Niederlander is the first author on this paper, which we submitted over the summer and we're revising now in response to the referee comments. And she was a sophomore when she did most of this work last year, a sophomore undergraduate. And Anna was a freshman this summer and taught herself how to run n-body simulations, and also worked on reproducing these different gap carving mechanisms that have been proposed in the literature. So you can have a planet embedded in the gap. That's the easy, obvious one. You can also have 2 inner planets in resonance that form a resonance chain that clear out gaps farther out in the disk. Or another interesting mechanism that was proposed for the HD 107146 system is that you can have an eccentric inner planet that's actually a low mass inner planet that if it starts off eccentric and it has a mass comparable to the mass of the outer disk, you basically get the disk will circularize the planet, and kind of as part of that process, the planetesimals in the outer disk will actually wind up inheriting some of the eccentricity of the gap, and they will become apsidally anti-aligned with the original orbit of the planet, and give you these gaps that can form and persist and travel through the outer disk. So there are various mechanisms, and so Anna not only modeled the HD 206893 system, 2 of those mechanisms, the inner resonant planets and then the inner eccentric planet with a mass comparable to the disk, are ruled out for the HD 206893 system because of the presence of the brown dwarf. There are just not enough stable orbits for those situations to take place. But basically what Anna did is she worked on reproducing all of these gapped disk models with all of the different types of mechanisms that have been proposed. And basically, to nobody's surprise, a single embedded planet per gap can reproduce all of the observations. That's easy. An inner eccentric planet can reproduce 2 of the 4, and in the cases where it didn't work, it was generally because the inner edge of the disk was too close to the central star to allow it to have the 2 resonant planets. There was just too much distance between the location where the 2 resonant planets would have to be and the location of the gap. And then and yeah, so 2 inner planets reproduce none of the disks because of the location of the inner edge, but an inner eccentric planet was able to reproduce 2 of the 4. So basically, this is following up on some of the theoretical work that was done by, for example, DJ Dong, who is one of Becky Dawson's PhD students at Penn State, looking at, okay, as we interpret these debris disk observations, a lot of people, and protoplanetary disk observations as well, a lot of people have liked to say, okay, well, where can we put a planet that it will reproduce the features of this debris disk? And we're trying to take that one step further now and say, all right, for these gap debris disks, we know where we can put a planet. An embedded planet will work, but will these other mechanisms work as well now that we're starting to have an ensemble of gaps in debris disks that we can study? And the answer is that embedded planets still work the best, but you could still have an inner eccentric planet that was low mass, that has about the same mass as the planetesimal belt, that can reproduce about half of the systems that we know of so far. And 2 inner planets with a resonance chain is not working for any of them because the debris belts that we're observing are so broad. So I'll pause there, and it sounds like there's a question.
Yes.
So that's a good point for pausing.
Yeah, good timing.
Yeah.
Dan, go ahead.
Hi, I was wondering if you can set any limits on the eccentricity of the debris disk from the observation.
Yeah, that's a good question. So we don't, it's a lot easier when you have molecular gas, I'll say that. And eccentricity in gas-rich debris disks is another area of interest of mine and something that I would really like to investigate. It's a lot harder when all you have is continuum, because there you're relying on really two things. You're relying on stellocentric offset. So can you detect an offset of the star from the center of the disk? And you're relying on looking for azimuthal brightness asymmetries like you would expect from that apocenter glow. So those are the two signatures that are relatively easy to observe with ALMA. And part of the problem is that at millimeter wavelengths, it's hard to see the star in a lot of these systems because stars are just faint at radio wavelengths. And so we don't get a good constraint on the position. But in general, the absolute astrometric uncertainty of ALMA is good enough to give us some limits. So as far as we can tell, HD 206893, we see no evidence for eccentricity, but the limits that we can place are not exceptionally good. I think it's something like, if the eccentricity of the disk were greater than around 0.1, we would be able to detect it, but we aren't able to say beyond that at the moment. Yeah, so it's trickier with dust. Gas is really interesting though, and I'm really excited about looking for eccentricity in gas debris disks and within a certain category. I'm particularly excited about it too, which is a whole other thing I could talk about, but I won't go into that right now. Yeah. Other questions at this point?
Next one, Bruce.
So when you're shaping the debris disk with these planets, obviously you're using gravity for that, but what other dynamics, what are you assuming about the motions of the particles in the debris disk? Are they being affected by radiation pressure, et cetera, Poynting-Robertson drag?
Yeah, so for the debris belts, for the particular debris belts that we are looking at, we are if you look at the timescales for Poynting-Robertson drag, this is something that when I was a postdoc, I worked a fair amount with Eugene Chang at UC Berkeley, and he is fairly convinced and has written a few papers about the fact that Poynting-Robertson drag for disks that have this high in optical depth is not going to be a dominant mechanism because the collisional timescale is so much shorter than the Poynting-Robertson drag timescale. So we're not really taking into account Poynting-Robertson drag. And we do include a radiation pressure term, but in general, it's so small compared to the dynamical timescales of these debris disks that it doesn't seem to be important for millimeter size grains. It's very important for the smaller grains, of course. And I'm actually going to talk in this section of the talk, I'm going to talk a little bit more about that wavelength dependence of where radiation pressure really starts to matter and where it doesn't. But in general, when we're doing our simulations, because we're looking at, when you look at the time scale for Poynting-Robertson drag and for radiation pressure clearing for grains of this size, it's very small compared to the relevant timescales for the dynamical processes that we're looking at. So we're basically just using n-body codes to model the dynamics of these systems because of the relatively high optical depth. They're still optically thin, but just basically the relative density of these disks, the collision rate matters a lot more than the Poynting-Robertson drag timescale. And then for the radiation pressure, it seems like it doesn't matter on the timescales that we're looking at for the particular grain sizes that we're looking at.
Thank you.
Yeah.
Scott?
So you've argued that gaps are ubiquitous in these disks, and the most likely explanation for the gaps is planets. So there's seem to be more and more evidence for planets at large radii. On the other hand, the direct imaging searches have looked at a lot of stars and found very few planets. So the two lines of argument seem to be pointing in opposite directions. And I guess I'm wondering how you reconcile the two of them.
So frankly, it's not hard to reconcile at all at this point because the parameter space doesn't overlap yet. Because the gaps that we're seeing, basically there's none of the gaps that have been discovered in debris disks so far could be carved by anything larger than a Jupiter. And most of the direct imaging surveys are sensitive to things that are larger than a Jupiter. So the mass ranges that we're talking about for the planets that we would need to be carving these gaps are at most 1 Jupiter mass. Generally, it's even smaller. And if there's eccentricity involved, it's even smaller than that. So we're talking about like Uranus and Neptune analogs, and none of the direct imaging surveys are even sensitive to Uranus and Neptune analogs out at these distances so far. Actually, the more interesting constraint comes from some of the microlensing surveys, which are starting to place constraints on the prevalence of Uranus and Neptune analogs, kind of the statistics of it. So that is actually encroaching a little bit more on the parameter space that we're probing than direct imaging surveys. But I'm not worried about direct imaging surveys at this point, because nothing that we would derive as being able to carve one of these gaps would be detectable by current sensitivity limits in direct imaging surveys. Yeah.
Okay, one more question, Christine. Christine?
Oh, yeah. I was just wondering, like, what percent effects approximately, or like what range of percent effects are the epicenter and pericenter excesses?
Oh, yeah. So it's small. It's, you know, and it depends a lot on the eccentricity. So, and it depends on some other things too. There's a great paper. Oh, I'm going to blank on the first author. So I know that Margaret Pan has written a paper about some of this stuff, and I'm blanking on the first author of the other paper that I'm thinking about. But there's actually a lot of really cool physics that you can learn about by looking at the apocenter glow at millimeter wavelengths. Now, the brightness asymmetry is pretty subtle. Again, it depends on all of these different factors, particularly the eccentricity of the debris ring. But it tends to be like at most a 50% brightness contrast. So you need really good sensitivity to be able to detect these relatively subtle differences in the brightness from apocenter to pericenter at millimeter wavelengths. It's not something that's going to jump out at you. It's not like a, you know, an order of magnitude brightness contrast. It's more like in the tens of percent level. Yeah.
That's all we have for now.
Okay, great. All right, so this next project that I'm going to talk about builds on some of these other themes, and this is one of my favorite tricks to play with debris disks these days. So in this section, we're using debris disks to weigh planetary systems, and by that I mean to try to get at the total mass of planetesimals and planets embedded within a debris disk, because we think, like I said, that these millimeter wavelength observations are tracing the actual locations of the planetesimal belts, and we think that there could be Uranus and Neptune analogs kind of hiding in some of these debris disks and planetesimal belts that we just don't have the angular resolution to look for gaps in yet. So we want to know, how can we get at that total underlying mass? How can we get at the total mass of planetesimals and planets that are sculpting these debris disks if we can't see them with, for example, direct imaging? So here's our idea. Now, I'm going to give you the cartoonish version of this. There are a lot of details, but the basic concept is actually quite simple. So for large dust grains, the vertical puffiness of the disk, whether it's flat like a pancake or puffy like a donut, is a probe of the total mass inside the disk. And here's the cartoon version. So if you have a Neptune or even a super Earth embedded in your debris disk, and you have random dust grains gravitationally interacting with it, it's going to give them kicks, and there will be some level of equipartition that happens between the eccentricity that's imparted to these grains and their inclination, and it will puff up your debris disk. Whereas if it's stirred by just a few Plutos in there, it should be pretty flat. And so basically, the puffier your debris disk is, the more mass is embedded in your debris belt. And so there was a great paper by Philippe Thébault in 2009 that looked at how the wavelength dependence of this effect, basically, like at what point because radiation pressure and stellar winds will also puff up your debris disk just naturally. There's actually a natural scale height that you can derive, and this was what Philippe Thébault's 2009 paper said. There's a natural scale height that you can derive from radiation pressure and stellar winds that predicts a particular height for the debris belt. And that natural scale height from stellar winds and radiation pressure is a steep function of wavelength, and it's very large at optical and near infrared wavelengths, and it drops off precipitously as you get into the far infrared and millimeter part of the spectrum, and it's essentially zero in the millimeter part of the spectrum, because the stellar winds and radiation pressure are just so much less strong for these millimeter sized grains. So if you look at ALMA wavelengths, the cool thing is, and this is from one of our proposals, the cool thing is that this method of measuring the scale height, now at ALMA wavelengths, you're really measuring this dynamical scale height that's imparted by the mass that's embedded in the debris disk. And this is a figure that came from some work that I've done collaborating with Margaret Penn and Hilke Schlichting. They have a model of the velocity of the grain size dependent velocity dispersion in the collisional cascade. So they're looking at, for different particle sizes, for different grain sizes, like these 1.3 millimeter-ish particles that we're looking at out at ALMA wavelengths, what should the velocity dispersion be for those particles with different masses embedded in the disk? And so it basically winds up being this relatively simple relationship where the flatter the disk, so this is the scale height that we're measuring here. So the scale height in arc seconds is closely related to the total perturbing planet and planetesimal mass in the disk. And now with ALMA at cycle 3, I think we wound up making more of these observations in cycle 4 and cycle 5-ish. I can't remember exactly, maybe cycle 6. We've done it now at 2 wavelengths, which I'll talk about later. But you can see from this that this is a very sensitive probe of the total embedded mass in the debris belt. And in fact, it's sensitive down to masses of just a few Earth masses, right? So this is way below what any direct imaging survey could tell you about the masses that are embedded in these disks. And so the first thing we did is we went out and observed the AUMIC disk at a wavelength of 1.3 millimeters, and we found that it was indeed quite flat. And that the upper limit that we were able to place on the total mass embedded within the disk is 1.6 Earth masses. Now, there are a number of caveats that come with that number. One of the important caveats is that we can't tell the difference between a single 1.6 Earth mass thing and a swarm of Plutos that adds up to 1.6 Earth masses. This is just giving us basically a total mass measurement. The other thing is that we can't rule out external perturbers. For example, there could be less than this mass embedded within the disk, but there could also be like we now know, for example, that AUMIC has a planet orbiting much closer to the star at I think it's 1 or 2 AU around the central star. And this is far enough out that its dynamical influence won't extend. So we can't say anything about things that are far interior to the inner edge of the dust disk, and we can't say much about things that are far exterior to the dust disk. But what we can say is that where we are able to resolve the vertical scale height of the dust disk, which is between radii of roughly 20 AU and 40 AU, so similar to where Uranus and Neptune are in our solar system, we can say that within those radii, 20 to 40 AU, there is no single body more massive than 1.6 Earth masses, which is a really interesting constraint that we're able to place. So we basically have no Uranus and Neptune analogs between radii of 20 and 40 AU in this system. So that's cool. And that was a paper by my former student, Cale Daly, in 2019. He's now a PhD student at University of Illinois. But we can actually go even further than that, and we can play this really fun game. So when we're talking about the physics of the collisional cascade, there are these 2 power laws that characterize the dust grain properties. One is that we can look at, this is kind of the one that everybody looks at in protoplanetary disks and debris disks, basically the number of particles as a function of the size of those particles, and it's characterized by this power law index Q. So people have looked at that for a long time. It's not that interesting. I mean, it is. It's very interesting if you care about dust. But what's more interesting and what hasn't been looked at before is this other power law, how the velocity dispersion V depends on the grain size. And so it has this other power law index P. And it's pretty important in terms of understanding the tensile strengths of the bodies in the collisional cascade, because it's basically telling you whether collisions in these debris disks are elastic or inelastic. So are you colliding dust grains together and shattering them, basically? Do you have these kind of fluffy aggregates that collide and shatter? Or do you have more like compact spherules that are bouncing off of each other and creating a velocity dispersion that's more equal across the different grain sizes? And so we can actually do that because, like I said, the grain size is proportional to the wavelength of observation, and ALMA has a really wide range of wavelengths that it can observe. So what we went out and did is we took our 1.3 millimeter observations and we supplemented them with ALMA band 9 observations at a wavelength of 450 microns. So that's about a factor of 3 in wavelength, which should correspond to about a factor of 3 in grain size. And what we found is, here's the 1.3 millimeter wavelength observation that I showed you before. Here's the 450 micron observation. And so we can look at the spatially resolved spectral index. It's actually fairly uniform across the disk, which some people who care about dust might care about. But then we were able to measure that power law slope of the velocity power law relationship. And we didn't really know where we would wind up. This was, again, a figure from our proposal looking at how these measurements of P and Q could help distinguish between, for example, the strength regime and the gravity regime, and also looking at this, once again, this physics of the collisional cascade. Basically, how does the velocity of the largest body compare to the velocity of the grain size that we're looking at? And what we found is that AUMIC, so this, we've only done this for one system so far. We'd certainly like to do it for other systems coming up, but for AUMIC at least, it puts us down in this corner down here where we're very much in the gravity regime. And it's telling us essentially that the collisions that we're seeing in this particular debris disk, which is not necessarily a representative debris disk, it's actually very weird in a number of ways. It's the only bright M-star debris disk that we know about, for example. But the collisions in this particular debris disk seem to be erosive collisions between grains of similar sizes, which is pretty cool. Partly because what the collisional cascade typically assumes is it typically assumes these highly destructive collisions, and that's not what we're seeing in terms of what we're seeing in the velocity dispersion as a function of particle size. We would expect that those highly destructive inelastic collisions would result in a much steeper slope in the velocity power law index, and we're seeing a very flat velocity power law index. So I guess I'll pause there and see if there are any questions about this project. And I think, there's a lot more that we can do here. Obviously, we've only looked at one system so far, but it's really fun because this velocity power law index has never been measured outside the solar system before. So I think that it presents a really kind of unique way of looking at the tensile strengths of dust grains outside the solar system.
Chris?
Yeah.
Hi, Meredith. I'm just wondering if so like you had that Q and P regime, would you expect that to be like different, closer in versus further out, where you have like CO ice versus water ice and things like that? And does that fit with what you see?
That's a great question. Yeah. So I think you could definitely expect that in different parts of the disk, where, as you say, there might be different ratios of different types of ices to the solids and the silicates that compose the dust grain, you might expect to see differences. And we can't say much about it given the observations that we have so far, because we really only are exploring this limited range of radii between 20 and 40 AU. And as far as we can tell, it's pretty uniform over this radius range of 20 to 40 AU. But it's definitely something that we could look at if we found debris disks that had, in fact, we might even think about targeting these debris disks with multiple belts if we can find ones that are sufficiently edge-on to do this kind of measurement, because then you could see if it does change through different parts of the disk. And that would be really interesting as a way of testing, does the composition of the grain or the tensile strength of the grain change with the ice to silicate ratio as a function of radius? That's a great question, but I'm sorry, I don't have the answer yet.
No, that's fine, thanks.
Jeremy?
Yeah, Meredith, this is great. You haven't said much about the ages of these systems, either the age in absolute terms or really the point of my question, the age relative to processes that remove grains of a certain size. So, yeah. I thought I had the general picture that in some of these treatises that Mark Wyatt talks about and so forth, you need asteroid-sized bodies or something as the sources of the dust. But let me put it this way: for the systems you're studying, these bright relatively dense disks, do you have a sense of what the smallest grain size is that could survive for the age of the system?
Yes.
Without being sourced by something bigger.
Yes, so that's related to this concept of the blowout size, which you can calculate for stars of different luminosities and for stars with different stellar wind rates. Even people have tried to calculate this for because AUMIC does actually have a relatively strong stellar wind. So I can answer this question in so many different ways, but first of all, AUMIC is very young. It's about 12 million years old. It's part of the Beta Pic Association, Beta Pic moving group. And so it is on the younger end. That said, when you make this blowout times this blowout size calculation, the timescales are pretty quick for removing them. Shorter than the timescales, depending on exactly how you calculate it, are around 1 to 10 million years. So in the range where you might expect these grains to be blown out on timescales shorter than the age of even these really young debris disk hosting stars. That said, the blowout size for is as you might imagine, it's a strong function of stellar luminosity, and there are some observations. We do have some observational constraints from people basically looking at large samples of debris disks where you don't necessarily so you have it's not like resolved on the level that I'm resolving here, but you have some resolved observations that tell you the location of the belt, and basically comparing that to the temperature that you get from the spectral energy distribution, and then deriving the minimum sizes of the grains, because of course when you have more of those small grains, you're going to have hotter grains, and so they will be located farther from the star than an equivalent disk that was at the black body equilibrium temperature. And so what people have found from those papers, I think there's one by Nicole Powelic, I think is the first author of that paper, where she's actually looking at that relationship and finding that you can really observe this relationship between the stellar luminosity and the blowout size of the dust grains. But the blowout size for most of these systems is in the range of like submicron to micron size. Like a few microns is pretty typical for a sun-like star, and it might be slightly larger than that for AUMIC, but it's not going to be anywhere near the millimeter part of the spectrum. So I don't know if that gets at the question that you're...
Not really. I mean, I appreciate the blowout effect, but
Yeah.
I was thinking of a sort of erosive size. I mean, given the brightness of the disk, you can estimate, how large the grains have to be so they haven't collided with anything their own size yet.
Mm-hmm.
And that must be a larger. It's not clear to me whether that. I mean, are the millimeter things already in the collisional cascade? Do they need a source that is bigger
Yes,
than
the millimeter things need a source. Yeah, for sure. The millimeter things need a source. Even the timescale for a millimeter size dust grain in one of these systems is still of the order of, I would estimate, it would depend on exactly which system, and I haven't sat down and calculated for all the different systems that I'm talking about, but it would be around 1 million years. So they should have been cleared out by this time. So the millimeter grains should be participating in the collisional cascade. They should be produced by these larger bodies. Yeah.
We have a lively discussion, although time is running out. So 2 more questions, and let's try to be.
I can also skip the debris disk gas stuff if we run out of time.
Christine?
Yeah, do you mind going back to the plot that had like the spectral indices?
This one?
Yeah. Can you point out where the solar system would be on this, since you said it was measured?
That's a great question. I have no idea where it would be the Kuiper belt in our solar system. I mean, the Kuiper belt and the zodiacal light might be different points on here, but that's a good question. I'm sorry, I really don't know, because I don't know the size distribution slope that's been measured in the solar system, although I would expect that it would be, I think it's pretty similar to like a Donaghy distribution, which would be more up here. AUMIC is kind of an outlier in that sense. So if I had to guess, it would be right up here. And then I know that the power law slope is steeper for the solar system than we measure for AUMIC. So my guess is it would be like somewhere in this range over here. It would definitely not be down in this lower corner, but I don't know the numbers off the top of my head. It's a great question, though. I should find that out and put it on the plot.
Thank you.
Yeah.
Bruce?
So 2 quick questions. What is the actual velocity dispersion that fits the thickening of the disk, or is the upper limit on the thickening of the disk?
Yes. So we actually do have a measurement. It's not an upper limit. It's like a 4 or 5 sigma measurement on scale height. And we calculated in the paper, and I'm probably going to botch it off if I try to tell you off the top of my head, but it is in the paper. It's in this Daly et al. 2019 paper that we wrote. Yeah.
And the other question is, it looks like you're getting its Q value about 3, which is very strongly divergent in mass at the upper end. So everything depends on having a mass cutoff.
Yes.
So are you not just seeing all of, everything being dominated by the largest particles? Are you really sensitive to the smaller ones?
What do you mean sensitive to the smaller ones in what sense?
You look, the ALMA observations are over a finite range of wavelengths, and it looks like you're very strongly dominated by what's going on at the large end of the mass distribution with this power law index.
With this power law index? Yeah. So AUMIC is unusual. Well, I should also mention, though, that this particular measurement of Q, this is a spectral index that does not take into account the fact that AUMIC is a much cooler star than some of these other stars since it's low luminosity. So we're up near the top. We're no longer in the Rayleigh-Jeans tail. So this hasn't been corrected for the alpha Planck that you would get from being up closer to the turnover of the black body function. So, so the true grain size distribution slope would in fact be slightly steeper, but AUMIC is really an outlier. Like if you measure spectral indices for all of these debris disks, it is truly an outlier along the low edge of the distribution. But I'm not sure. So I'm not sure I understand exactly. I want to understand your question better. But yeah, I'm not sure if it makes sense to go back and forth now, or maybe we should talk after the talk. Yeah.
Thank you very much.
Yeah.
Okay, that's all the questions for now.
Okay, great. So maybe I'll just kind of briefly mention, so this is actually a very simple project. So I'll just give less background than I would normally give and then just show you the results. So basically, like I mentioned, we find these, so you can observe gas in all kinds of different formats in debris disk, atomic, molecular, via emission or absorption. We've seen all of them. These are just some examples. And then this is again from our annual reviews article looking at the prevalence of gas in debris disks. And this hasn't been corrected at all for the varying sensitivity of these surveys. It's basically just a snapshot of, okay, if you go out and look for gas, how often do you find it around different types of stars? And the answer is you find it a lot around young A and B stars. You find it around some FGK stars, and interestingly, there seems to be less of a bias between young and old FGK stars, but young A and B stars are where you mostly find it. And then when you look at how bright it is as a function of the age of the system, you find that there is this population. So you can see the A and B stars, once again, are separated mostly out into the top of this plot. A and B stars are the circles, and the FGK stars are the triangles. The colors are the things with gas detections, and the triangles are upper limits. So when you're looking at these gas detections, you're seeing a population of mostly bright A and B star disks at young ages, and you're seeing a population of fainter FGK stars that are at a wider variety of ages. You see a couple of these older systems, and the older stars tend to be both fainter in terms of the amount of the fluxes of the carbon monoxide that you're measuring, and they're less axisymmetric. So in these older systems, we tend to see more azimuthal asymmetries. And the question is, what is causing this phenomenon of gas in debris disks? So there are basically two possibilities. One is that it's protoplanetary disks that are refusing to grow up and disperse their gas, even though their dust has transitioned into the debris disk stage. But we have a lot of constraints about how dust evolves with time. We have a lot fewer constraints on how gas evolves with time. So it's possible that these are just remnant protoplanetary disks that are waiting to disperse their gas, that have a longer gas dispersal timescale. Or it's possible that the gas is a second generation phenomenon similar to the dust, where you have some kind of collisions or photoevaporation that's liberating the gas grains from comets or icy mantles of dust grains at later ages. So those are kind of the two categories that these explanations fall into. So I asked this question, I did this survey as part of a discussion that I ran last fall for a debris disk observers workshop. And you know, it was actually pretty evenly distributed between all four of the options, either exclusively primordial. Actually, I don't think there were many people who thought it was exclusively primordial. I think some people thought that it was exclusively second generation. Some people thought it was probably a little of both, that some of these systems, especially the older, more asymmetric ones, might be second generation, and then some of the younger, brighter ones might be primordial. And then a lot of people are just not sure and are kind of waiting to see. So that's sort of where we are as a field in terms of our knowledge. It's really kind of a toss-up between these two. I think it's pretty clear that some of the systems, especially the older non-axisymmetric ones, are second generation, but we really don't know about the younger, brighter ones. So one piece of the puzzle that we've added recently is we went and said, okay, what is the chemistry of these things? We looked with ALMA and we wanted to see, all right, let's look for some molecules that we expect to be prevalent in protoplanetary disks and that we expect to be prevalent in comets. Like methane is very prevalent in comets. HCO+ is in both protoplanetary disks and comets. HCN we see a lot of in, again, both protoplanetary disks and comets. SIO we might expect to see, it just happened to be in the band, so we looked for it anyway. We might expect to see it if, for example, you are really like collisionally vaporizing dust grains, which may or may not be the case, but we thought we'd look for it anyway. And CN had been predicted to be very strong because of its photodissociation lifetime is very long, even compared to carbon monoxide. So we basically looked as deep as we could with ALMA, a 5-hour observation with 2 different correlator configurations, and we saw nothing. And that was a big surprise, in fact, because if it was a protoplanetary disk, we should have seen some of these molecules. We should have seen HCO plus and HCN. And if it were a comet, we should have seen some of these other molecules. We should have seen at least HCO plus and methane, for example, and we saw nothing. And so the line ratios are neither comparable to protoplanetary disks nor comets. But what was kind of going on in the background while we were doing this survey is that there's this sort of new piece of the puzzle that's come in with some of the modeling that's been done of potentially second generation origin of CO. And that involves shielding by neutral carbon. And it just turns out that neutral carbon, which is of course a photodissociation byproduct of carbon monoxide, neutral carbon can actually prevent further photodissociation of carbon monoxide. And I think that's a fact that's actually been underappreciated both in circumstellar disk modeling and in interstellar medium modeling. But that really seems to be what we're seeing here, is that as the CO is photodissociating, the neutral carbon is actually preventing, it's shielding the CO that's left in the disk from further photodissociation. And basically all of the other molecules are getting photodissociated. So unfortunately, this doesn't really tell us whether it's primordial or second generation, but it does tell us a little bit more about the underlying mass of carbon monoxide and a little bit more of understanding of the lifetime. And it is actually plausible with this neutral carbon shielding that you could have at least carbon monoxide, if not all of the other molecular species, but at least carbon monoxide could persist long after the protoplanetary disk phase and have a much longer lifetime than some of the other molecules in the disk because of the shielding by neutral carbon. Okay, so that was really quick for that one, but just to summarize, debris disks look different at different wavelengths. They probe companion masses and origins. We can place these constraints on the total mass embedded in the disk, and observations at widely separated millimeter wavelengths seem to imply, at least for the AU mix system, erosive collisions between grains of similar sizes. And then finally, gas and debris disks is common, especially around young A and B stars. It could be primordial or second generation, but the shielding of CO by neutral carbon does seem to be extending the lifetime of the gas, at least the carbon monoxide gas, relative to the other species in the disk. And I'm happy to stick around and take any other questions that anyone has, but thank you all for your time and attention.
Awesome. Thank you for a very interesting talk. Seems like we have exhausted our questions during talk, and we are already running late. So if no one has an urgent question right now, then we can end here. We have about 23 minutes until lunch. So make sure you go there. Do not come back here. The call lunch is a different link. Check your emails. And thanks again.